Okay. Green light is on. Welcome to the last face-to-face for Metabolism for 2019. It's cocktail time, isn't it? Next week, where are we? Blackboard collaborates. That'll be recorded as well. Now, before I get underway, a number of people, not a huge number, but a number are asking for a Q&A tutorial in StuVac. See the heads going. Q&A tutorial, we'll make it the same time as the exam. Exam's Tuesday, what time? Sorry? 9:30. 9:30, so Tuesday, StuVac 9:30, 2 hours. I'll put a notice on views. I'll just remind your colleagues at Parramatta and Hawkesbury, rather than making it the lecture time, because you don't have any lectures after that, I assume. And then you know you've got a week to prepare for the exam. If you are looking at those guiding questions, you might want to make sure you've gone through them in detail, because 2 hours I'm not going to go through all the answers, and as always, multiple choice the answers in front of you. So you just need to work out what it is. At the end of today, I'm going to give you some hints on assignment part B. I'm going to say now and then during the break as well that this week for this campus, those of you who are doing the labs down here, you'll come in, you'll have your cortisol assay under your arm, you'll have your protein assay under your arm. You'll come in, you'll get 2 samples. You'll get a protein sample with your patient number on it and a cortisol sample from saliva with your patient number on it. You'll be given those. Once those samples are in your hands, NMP. Is that kind of clear? If you spill it, lose it, whatever, that's not our problem, that's your problem. It's your responsibility to look after your sample. You'll get a 96-well plate to do your protein assay. Which protein assay are you doing? The Bradford, the Sigma assay. Make sure you read and understand those principles. You've done protein assay all semester, developing one. The cortisol assay, which one are you doing? Salimetric salivary cortisol. Very nice, straightforward, competitive ELISA, can be done in 3 hours. That's why I use it. Not exactly cheap, so the demonstrator will be doing the standard curve. You'll get little rows of 8, come out of 96 well, broken in half. 4 wells, 2 for you, 2 for you. You look after them and you'll add things, wash things whenever the demonstrator says. Is that kind of clear? The demonstrator will conduct and orchestrate the cortisol assay. You can do the protein assay as many times as you like, that's up to you, but when the 3 hours is up, 3 hours is up. Is that clear? At the end of that 3 hours, you'll have your protein standard, your protein unknowns for your salivary protein. Almost guarantee someone's going to mix those samples up. You can do that, but you might find it doesn't work as well. The other thing that we'll have is a standard curve for your cortisol assay. We agreed last week across all 3 campuses that you will have from the end of your lab session, so if it finishes at lunchtime or 5 o'clock, 24 hours till the end of that time to submit to views your cortisol concentration for your patient and your protein concentration for your patient's saliva. There are 2 multiple choice questions you're going to get based on the protein and cortisol assay. If you haven't read those protocols, it might be time to now. Is that kind of clear? There's no lab book marking, nothing else. If anybody has not been a team leader, I have not granted exemption for team leaders or special consideration. Anybody who needs to be a team leader who missed out for whatever reason will have to do it in front of me next week, more than likely Thursday. You'll need to advise me if you need to. If you don't advise me, then you won't get to be, which means how much disappears off your assessment? 5%. There's no missing out on team leader, I'm afraid. We're ready to get rolling on the last formal lecture for metabolism. I can roll it back a bit and do a few more if you want. Okay, what we're dealing with today is more like the stuff where we're looking at the real world. You've hopefully seen in the media, if you ever read the news, huge issues of diabetes and particularly obesity in this country, expanding exponentially. I keep threatening that's an issue. You should be aware of that as metabolism students. What I'm also preparing you for today is the exam. Now, I've got some stuff coming later on today which relates to how your report should be focused, particularly for report part B, which is slightly different, not exactly the same as report part A. In the exam, one of those short answer questions talks about the fed and fasted state, doesn't it? Let's look at this simple schematic. Some people draw this in the final exam to get an idea of what sorts of things to discuss in that kind of question, because you have a line page you can write and a blank page you can draw. You can draw on the line page if you wish. In this case, we're looking at the fed state. So what do you look at the beginning of the semester? We look at incoming glucose, incoming amino acids, incoming fats. What do you have to do with those? Well, if they're carbohydrates, you've got to break them up. If they're fatty acids, you've got to break them up. Amino acids, you have to break them up. You absorb them across that gut layer there, that epithelial layer. Amino acids and glucose went via the bloodstream, didn't they? Fats went via the triacylglycerol system, which is in chylomicrons, through the lymphatic system, and then they get distributed around. When you run through the blood system, this character in the middle, which is who? The liver, write it down so you don't forget, is going to decide what to do with this stuff. It's going to say, well, I've glucose, I need to fill up my glycogen stores, make sure the brain keeps working, producing its energy activity, and any excess I'm going to turn into fats. I'm going to turn any of that glucose into fats as excess energy. We're going to see on today, if the demand is high, you can't go through that process, you're going to turn it into ketone bodies. Those ketone bodies come from various sources. You've turned it into triacylglycerol through malonyl-CoA, a glycerol moiety. You package them up, and that package coming from the liver are VLDLs, aren't they? Unlike this, the chylomicrons. Make sure you write it down there. You remember chylomicrons from the gut to the lymphatics. Those things run around, and eventually you keep sucking fats out. They get smaller. You get ILDLs, HDLs, and so on. Those VLDLs, if you're under the fed state, remember this is the fed state, where is most of them going? The fat storage. What about your amino acids? Well, if you're not in a growth phase, having a baby, you're in a repair phase or defence mode, what are you doing with those? Turning them into fat. But you've got to take the nitrogen off, which is the urea cycle, isn't it? Understand these keto acids, put down there in case you get into a fasted state, particularly long periods we'll talk about today. The trouble is, in this part of the world, we tend to eat a lot more than we need to, because things are easy to get and we don't tend to exercise as much as we should do, because we don't sit on our phones doing all sorts of things. So for this particular fed state individual, what we're looking at, well-fed person with lots of glycogen being synthesised, lots of fat synthesised. So it's glycogenic, glycolytic and lipogenic. Please note those terms. Small point here, which is in the media on the weekend, is the number of individuals. You can see there now more than 63% of our population is pushing obesity. It's actually higher in children. It's increasing in children. You need to watch what children do over time, because once you get those fat cells, you don't lose them, do you? They just increase in number and they can increase in size. This is the fed state. Are we comfortable with this one? Here's a table which makes life very miserable in lots of ways, but what's it for? Well, we're looking at the different types of hormones and products, that is, things like glucose, fatty acids. Down here, this acetoacetate, the beta-hydroxybutyrate, put a circle around them and write ketone bodies. Those two, acetoacetate, hydroxybutyrate, are ketone bodies. Like all things in you, there's not really a zero concentration of anything. There's always small amounts coming out all the time. It's the relative ratios. And that's the key thing for this table. Let's look across the top here. The kinds of molecules we're looking at, we run from insulin, glucagon, we can look at a ratio. We're looking at fats, we're looking at glucose, we're looking at lactate, depending on what the individual is doing, pyruvate, alanine, and ATP equivalents. Let's run across the top. In a well-fed person, post-absorptive, 12 hours, when would that be for you? After a good night's sleep, maybe? Fasting for 3 days. Anybody fasted for 3 days? And I mean full 24 hours, 3 days, not just a few hours. No. And then for 5 weeks, could you last 5 weeks? Well, you probably could. Look at those runners, particularly the Kenyan one that just won the marathon under 2 hours. There's no body fat on that character. What do you notice? Insulin, fairly high in the well-fed person, no surprise, drops down to less than half, 12 hours. Still about half, roughly 3 days, and then not much less after 5 weeks. It doesn't get to zero. What about our glucagon? That goes up and up and up. Doesn't keep on going up, it stabilises out. We'll see that later on as well. What about your glucose levels? After a meal, now I'd write down it depends on your meal, how much is glucose or carbohydrates in that meal. Relatively high for, say, 12 hours, didn't jump too much down. 3 days, still pretty constant. 5 weeks, still pretty constant again. So it doesn't get to zero. Your liver's busy trying to maintain some blood glucose level for who? Your brain. Fatty acids, well, you can see they tend to increase a bit. They should depend on what's in your meal as well, but they start to increase the more you're fasting. You're releasing them from fat stores. They're becoming more accessible for muscle activity. What about these ketone bodies? Well, they're relatively low. Obviously, during the fed state, they creep up a little bit and a little bit more. What you want to note is beta-hydroxybutyrate is the one you use the most. Acetoacetate, not as much, and there's another one called acetone you actually exhale, vaporizes. What about these others? Lactate declines over time, never to zero. Pyruvate declines, never to zero. Alanine, always some, but never to zero. And your ATP equivalents actually looks like they go up, don't they? So you're trying to maintain ATP, that is the energy level for that particular individual. And this depends on what you eat. Please note that. Depends on your age, your body mass, what you eat. All of this is slightly variable. The key issue here is what happens to you over time. You don't get to zero for anything. Can I get to the next one? Okay. Remember I talked a bit about this one last week. I asked you to keep the concept in mind. Well, the concept now is if you've got lots of energy, you're growing, having babies, defence, repairing, then you're going to be inducing some of these events. So is the incoming nutrients, those carbohydrates, those fats, those amino acids, they are available energy for growth, for repair, for replacement. We talk a lot about next semester in advanced cell, a lot of stem cell work next semester. And stem cells, like most of your tissue, requires growth factors. We've seen some already, like growth hormone last week. Insulin is a growth factor. It stimulates growth because cells can take up glucose for work to grow. And I mentioned those stimulate this mTOR, which is a serine threonine kinase, a key regulator, a master controller. What does it control? Well, lots of the glycolytic pathway, including the pentose phosphate, to make nucleotides. You need nucleotides, DNA, RNA, if you're making more cells and cellular components. Not only that, if you start to increase muscle mass, increase the size of the individual, make babies, you need blood vessels, hence the angiogenesis. And this hypoxic inhibitory factor, because your cell mass gets bigger, inducing the HIF release. It also induces mitochondrial metabolism. It says mitochondria get busy because there's incoming, you need to make energy to do the work. No surprise. And these, remember the PPARs? That's coming back again this week as well. Those peroxisome-related receptors, they coordinate tissue so that you don't have one tissue doing one thing, making fat, another one breaking it down, for example. All of these are to help make more lipid membranes, not just the cytoplasmic, the nuclear, vesicles, ER, everything else when you make more cellular components. So all of this, just please underline cell growth and proliferation. Your gut has to replace cells every 5 days. You have to replace a new blood cell every 5 to 6 months. Bones every 5 to 11 years. Skin cells every 4 or 5 years. You're constantly replacing cells, which is growth all the time. You're not the same person you started to be. Things are always changing in you. What does change a lot of these steroids, and you're doing the cortisol assay next week, or this week I should say, on this campus, doing the cortisol assay. It's a stress hormone, write down chronic stress hormone. But like these other steroids that you see here, testosterone, estradiol, even aldosterone, prednisolone, those guys are transcriptional regulators. They're going to alter what your mTOR does. So a chronic stress might impact on what mTOR does to stimulate growth. It might be pushing it one way, fat deposition, or might be pushing it the other way, which is more anorexic. Bless you. We comfortable with this one now? Okay. Let's take you through a fasting state. Before I do, are we all familiar with the term glycemic index? There's a web link. I'd encourage you, all of you, as university students, young people about to take on the world, look up glycemic index. It's a useful tool, not the absolute tool. What does it do? It gives you an indication, and I mean indication, of what your foods you eat in terms of the glycemic index, whether they punch up glucose or bring it down. Do you know how they measure glycemic index? Anybody? Sorry? Yep. After what and on who? But that's right, it's a blood test, yep. Generally they take a blood sample from half a dozen people before mealtime. They give them a particular foodstuff. They monitor their blood glucose, usually 10 or 15-minute intervals for a short period of time. They watch the glucose rise and decline, and they average it across those half a dozen or so individuals. The glycemic index you want to jot down on this slide is the area under that curve. So it's not just the peak value, how quickly glucose gets into their blood, it's actually the area under the curve and how long it lasts. And I hinted at last week, Romans used a different diet to be able to march longer, work harder, without having a high glucose rush. Yes, mate?
In order to test like these 40 people, they have to be like almost identical, right, to get the...
That's a good question. These half a dozen or so people have to be identical? Not absolutely. They are generally random individuals, sometimes the same age bracket, same sex, but they're usually randomised. And that's because we're all different in how we deal with blood glucose, isn't it? How we use our insulin, our glucose receptors, what we eat, what we're used to as foodstuffs, which is going to change our metabolism. So let's go back to this slide. All of these components, this metabolic pathways, will impact on that particular analysis, won't it? That's why it's an average of 6 or so people over a time frame, and it's an area under the curve. Does that kind of make sense to your question? Okay. All right, what are we looking at here? Well, you've just been fed, now I'm going to fast you. We know you've got a few days to go. Let's have a look at what happens to you as you go through the process. So you've got blood coming in. Where is it coming from? From your gut. Who's using that glucose? Everybody. What's the major fuel for your brain? Glucose, which is phase 1. Look at phase 1 here on this particular graph. You see the numerous Roman numerals. Phase 1 is this first 4 hours. Didn't I say roughly 4 hours before you go for another meal? So now we've got phase 1. So it's mostly exogenous. You've got down here, now suddenly you have another meal. What if I don't let you have another meal? No chocolates, no lollies, no snacks. That's it, we're going to fast all the way till the exam. Let's do that. So now we're going to phase 2. Phase 2 is between 4 and 16 hours. What are you doing here? Your origin of blood glucose is coming from glycogen and particular hepatic gluconeogenesis. So glycogen stores, there's my ATM being rated. Now I'm pushing back up gluconeogenesis to try and keep my glucose up. Bless you. Who's using glucose? Everybody except the liver, because it's pumping glucose out. Have a look at this, 4 to 16 hours. So there you see glycogen as the major source. Please note that hump there. And you see the increase in gluconeogenesis to roughly 16 hours. Let's go to phase 3. What's going on here? Blood glucose, our liver's still busy with gluconeogenesis, and glycogen. The two have switched around now. Let's look at the graph. Phase 3, what are you seeing? Glycogen's on the depletion road. Now what's taken over proportion is more gluconeogenesis because you're depleting your glycogen stores, gluconeogenesis. What I want you to note is you didn't delete all your glycogen and then start gluconeogenesis. Does that make sense? The two are kind of crisscrossing. I'm releasing glycogen, I'm increasing gluconeogenesis. As my glycogen stores come off, I start punching out more glucose from gluconeogenesis. Does that make sense? And what state are you in now? Fasting state, jot it down. What happens now in phase 4? Where are we in phase 4? We're actually just over a day or so. We're heading out to a number of days, almost a month, 24. What happens? Gluconeogenesis declines a little bit for those first few days and then generally flattens out. Let's have a look over here. Gluconeogenesis is on demand, mostly liver, and who's come in to work? Your kidney. Told you the kidney won't do anything until things get desperate. Well, now things are getting desperate. Who's using glucose? Your brain, red blood cells. They have no mitochondria at this stage, your red blood cells. The renal medulla, particularly because it's working hard trying to pump things through. What's the major fuel for your brain? You'll see glucose, and now ketone bodies are coming into play. We get out past a month or so, what happens now? Gluconeogenesis still, the liver and kidney still working away, our brain's doing the same thing, and you'll see ketone bodies are predominating and glucose is not as high an activity level in terms of helping your brain work. Your brain function would be dropping right off at this stage. Your decision making would be really poor. As long as you slept. Yes, mate?
Yeah. The glucose, would that be prioritised for other tissues, like fuel for other things, or is it just that it's dropping off now because you don't have as much?
It's generally dropping off because you don't have as much. Other tissues, which is a really good question, other tissues, particularly muscles, will tend to be taking more fats and use those, because I'm going to talk about the free fatty acids you're releasing while you're going through this as well. The brain's really good at sucking up glucose, okay? So it'll do that preferentially. Ketone bodies can be absorbed pretty quickly. But very good question. Can I move to the next one? Okay. And let's think about this individual, particularly if they're diabetic, and we're going to talk a bit about this. Your blood glucose, well, what's your liver doing? Trying to punch everything back and send glucose out into circulation. It's normally determined over a number of hours, usually several or so. And over that time, your blood glucose levels can change. And that's why I've got this little graph down here, or this chart, showing your blood glucose. Now, please note, this is an average blood glucose level for an average person. It varies slightly, so you have to be aware of the individual, their size, their body mass, what they eat, and so on. The normal range, you might want to circle that, between 60 and 90 mg per 100 mils. Please note, while we're on the units of measure, what's the cortisol measuring in that assay? The cortisol assay I've asked you to use. Talk something like decilitres. Make sure you know the units of conversion, because on views, I'm not asking for the same unit that that particular kit assay is asking you for. So what we have here is the normal range. What happens if you get below that 60 mg per 100 mils? Well, we start to see subtle neurological signs. You will get hungry. I was driving down, I was getting hungry, feeling a bit rumbling, so I have to go and have a chocolate or something, a hot chocolate, to get me through the day. What happens to you? You start releasing more glucagon in that case, and adrenaline. You get a little bit nervous. Cortisol's coming out as well. You start sweating and trembling. I was sweating in the car because it was hot, but I wasn't trembling yet. But that will start to happen to you if your blood glucose is down below that 60 mg per mil. If you get down around the 40, you'll notice there's a dark red line there. Put a line through that. That's when we see lethargy. You can't make decisions. You are sitting around. You often see convulsions. Brain function starts to really be impaired. I had a colleague at Scripps when I was working in the US. She lived on her own. She had this event happen during the night. We found her the next morning, unfortunately, and she wasn't with us any longer. Being aware of that state, often having alert systems like animals or alert systems to monitor blood glucose is critical, because you will die within 24 hours, which is what you see down here. And if you don't die, you often see permanent brain damage, because your brain does no longer work under that diabetic state. So this is the overall value. Now, it changes a little bit based on your sex, your age, your body mass. Please note those when we talk about individuals particularly. I'm going to talk about the body mass of an individual shortly. Can I move to the next one? Okay. Now, when in this fasted state, you have a number of reserves. Again, it depends on your body mass. Now, everybody's different. Don't expect you to look like Kipchoge, who just won that marathon with no body fat at all. That's not healthy. Indeed, he's going to have a great number of joint disorders very soon in his life. He doesn't think as well as he should do. All those things are going to catch up with him. Some body fat is important, and everybody's different how much body fat they have. So your energy reserves, and this is for humans mostly, and notice I've dotted in red some key ones. The fat from our fat cells, around 1,500 grams of fuel reserves. That's to guide you through lean times normally. It's not an unhealthy thing to go through a fasted state. The amount of protein, well, it depends. Put a circle around the 6,000 grams on your body mass. If you're male, if you exercise routinely, that will change. And it can change fairly quickly. Those of you who go to the gym, you'll notice you don't go for a few days, suddenly, oh, God, that's hard work, and then suddenly it all disappears. Whatever that gun was, it's not there anymore because it disappears very quickly in that context. Remember, protein first and then fat. So these are all issues for you over time, and maybe we should talk about different diets while we're here. You've heard about those 5-2 diets, those ketogenic diets, all those other diets, high protein, high fat diet. Most of them are rubbish, as you know. The key issue is balance. Now, the 5-2 diet tends to work better. Anybody know why or might understand why? You know about the 5-2 diet? What is it?
Normal eating for 5 days. And
Whatever normal is, yep.
yeah, and 2 days, not consecutive days.
Can be consecutive days.
I think
Yep.
it's 500.
It varies. It can be either no food or water and dry biscuits or whatever low calories you like. Why do you think the 5-2 diet tends to have better outcomes than a lot of those other crazier diets?
It's a lot more sustainable.
Partly, yes. Remember last week I was talking about training your brain and your stomach? The 5-2 diet enables you to start to shrink your stomach slowly, particularly on the days of fasting. At the same time, your brain feedback from those hormones we saw last week starts to resolve. You're down-regulating receptors, you're starting to control that. So you're training your gut, your stomach and your intestines and your brain at the same time. I didn't just mean brain hormonal function, I mean receptors, signal transduction, all those events. So the 5-2 diet is a way to push yourself into that. It's a useful one to get you to think about shrinking your stomach naturally rather than going through stapling or sleeving, which some people do, because once you do that and you don't adhere to a strict diet, that's just going to stretch again. And your stomach is enormously capable of stretching. That's why you see those eating competitions. They can shove whole food loads into the TARDIS. Well, it's all in there. It's just stretched your stomach. That means the signal back to your brain, as we saw last week. Remember those hormones from last week? Ghrelin making you hungry. What was the other one that feeds back to try and inhibit you eating? Sorry? Time to review notes. When's the exam? 3 weeks. Want to review those. So think about how that trains you. Not just what you do, but also it trains your mind to resist temptation. So when ghrelin's rumbling away, trying to tell you to eat, you think, well, I've only got another few hours and then I can eat. What is interesting on those 5-2 diets is when you fast for 2 days, for whatever regime you fast for, when you come back to the 5 days, did you notice you don't kind of binge eat? Generally, you do not. And the reason is because you're shrinking your stomach, your brain's getting the signal, which is what we've been talking about, the signal back to the brain to try and inhibit the eating process once you've had enough, once you've had your fill. Can I move to the next one? Okay. And this is that fill. Don't write anything down, just look at the table. There's a 70-odd kilogram person. I'm 71 kgs. If I fast, how long can I last? It's over here. 3 months, I'm toast. That's it. An obese individual who weighs almost double what I weigh, how long can they last? Over a year. Now write down as long as they have, water, vitamins, minerals. Key things they cannot live without. You can't fast them with nothing. That's kind of critical. What it does tell you in this table is that that's an adaptive advantage. Like bears hibernating, like seals, all those other species, allows them to get in when they can, get the food when they can, and survive for longer periods. We've just changed our diet regime. That's what we've done. Can I move to the next one? Okay. Is this the fed or the fasting state? What's missing on this schematic? What's missing over here on the left-hand side? Your gut. It's the incoming. So this is the fasting state, isn't it? There's my glucagon. We're going to see insulin in a couple of videos today. What's it doing? Telling my liver, punch out glucose. Punch it out and get the brain to use it, hopefully. But also, when we fast longer, we have to go pushing out ketone bodies. We've seen a couple already. Acetoacetate, beta-hydroxybutyrate in those contexts. What are you also doing? You're telling your fat cells to start releasing fat. Now note, they tend to do it slowly. Not just rush all out these fatty acids, get busy, send them out. That would be detrimental to your bloodstream. So you're releasing fats at a steady, constant, slow rate. For this fasting individual, it's gluconeogenic, ketogenic, and not immediately. It takes a few weeks or days, I should say. And proteolytic, what does that mean? You're breaking up proteins. Your amino acids, that is in your muscle that you're not using. Write down not using. If you use it, you won't lose it. That means it goes all back to the liver and the liver decides what to do. Now, you might recycle some of these as amino acids. If you're recycling amino acids as glucose molecules or ketones, what happens to the nitrogen? You recycle. Jot it down. Need to connect these back up. That first slide and this slide is basically a summary of this whole unit, isn't it? The fed fasted. Is this fasting a stress state as well? Yes, I'll let somebody answer that. Indeed it is. And the longer you fast, the more stressful it is, isn't it? We're done with this one. Okay. Didn't we see these last week briefly? And I asked you to think about the concept. Because back here, these tissues need to coordinate their events. Who's coordinating those apart from the hormones? These characters, PPARs, peroxisome proliferative activating receptors, that's how they were found. That's why they've got that crazy name. Just think of them as PPARs. We saw mTOR affecting them. That is to get you to make more lipids, to make more lipid bilayers in your cells. Down here in ligand, last week I hinted, I want you to write down there, free fatty acids. That's the ligand. It's not a hormone, that ligand is free fatty acids. Let me go back here, oops. Free fatty acids you're releasing from these fats. You're releasing them from these fats, so these particular ligands get through the lipid bilayer, they get into this cell and they hook up with this protein, this big long red finger, and a pink one. They form these dimers. You're going to see some crazy stuff today. And they coordinate within those tissues to make sure whatever you're doing is consistent with other tissues, other activities. A few of them have been found. Here's PPAR alpha. Alpha and delta, and the closely related one, beta, regulate lipid utilisation. The gamma regulates lipid storage. What are you doing all of these? And you see in this little schematic, you're looking at the turnover back to liver, from the fats back to fats, and here the insulin sensitivity of your muscle cell. So overall, PPARs make sure the cell's internal activity is coordinated with other tissues around your body going through either the fed or the fasting state. Now, PPARs you see more in the fasting state or the growth state. Let me go back a couple of slides to make sure you recognise why. Remember our PPAR here? Adipogenesis, more sterols, more lipid bilayers, making more cells, particularly stem cell production. Are we more comfortable with this one now? There's more PPARs in the alpha, beta, gamma and delta, I'm afraid. There's different variants, but recognise free fatty acids coming from fat cells are the ligands that get into these cells to coordinate. Think about that for a moment. Let's go back to this slide. If I'm releasing free fatty acids, who's going to use them mostly? BSA, if you're a cow, will grab the fat. HSA, if you're a human, will grab the fat, carry it to a muscle cell. Usually it's not far away. That's why your fat depots are close to the muscles, except for the stomach, which is kind of why we worry about belly fat. When you release those fats, they don't just go to muscle cells. They distribute around your whole body. And when they distribute around, they can get into these cells, like we see here, into these cells through the lipid bilayer and affect what the cell does. Note that's all cells, not just muscle, not just fat. All cells are getting free fatty acid ligands to coordinate these PPARs. Does that make sense? Indeed. So then you've got coordinated tissue activity where? Well, here particularly at the gene expression, where you want to alter what those cells are doing. Not just the cell machinery, but make the right cell machinery to coordinate that event. Can I move to the next one? It's okay. I'll rest my voice. Right now, you guys right? Yep. Okay. Now we're getting more and more fasted. How many days did it take us to start really making ketone bodies? Where do we see ketone bodies starting to really pick up? Phase 4, which is about 2, 3, 4 days. Didn't take too long, did it? Now again, write down that depends on the individual. What are these ketone bodies a function of? I'll let you write first, but think about if I'm running through glycolysis, the citric acid cycle in the mitochondria, all of those steps take time. If I'm trying to go back gluconeogenesis, it takes time. What does my liver have to do? Produce something for the brain quickly, especially after a couple of days. Sorry. Can we talk about this one now? Okay. This is a liver cell. Here's a liver cell. What does a liver cell do? Pretty much everything. Jack of all trades and master of all. The liver's going to be making glucose from what? Glycerol, amino acids, take the nitrogen off. Those I can make glucose with. I'm doing that all the time. Liver cell's always doing that. But you're releasing free fatty acids. Let's go back to this slide. You're releasing more and more fats the longer you go out into that system. So what are you doing here? Let's get back to this one. You've got incoming fats. Yes, my muscle uses them, but now the liver's saying, the problem is to turn that fat into something useful like glucose, I've got to go down beta oxidation in a liver cell. Where does that occur? In the mitochondria. That takes time to get it in there. Remember, carnitine across and back across, reshuffle, get it ready. Now in my mitochondria, to get that 2-carbon-CoA into something useful, I've got to run around the citric acid cycle, bleed OAA out, run it to glucose and run gluconeogenesis. Right down here, that's gluconeogenesis. So I've got to go down the bottom, round the roundabout, back up, and then I'm also kind of sucking out of the citric acid cycle. I'm making glucose from fat, but I've got to run all the way through that system to do it. That takes too long. So what do? Well, I get to acetyl-CoA, and from it, I bypass the citric acid. I'm now making ketone bodies. These are the 3 main ones. Make sure you know them for the exam. Acetoacetate, hydroxybutyrate, and acetone. Those enter the circulation. Heart can use them. They will use them when they're getting desperate. Matter of fact, it takes up a large proportion, as I indicate down below. Can get up to 70% beyond the 3 or 4 day period. So heart's good at using fats and ketone bodies when things get really bad. Can I get to the next one? Bit of grunt biochemistry, gotta love it. But one thing you're going to circle is that HMG. Remember last week there was this pathway where we had adiponectin affecting a number of enzymes. One was HMG. I asked you to note HMG. Well, now that's why I asked you to note HMG. Because if we start up here, now don't write anything, you look first and I'll explain. What do you see up here? No typing. Acetyl-CoA. There's a 2-carbon CoA. What's this thing? 2-carbon CoA. Shouldn't they do something? They can come together. In a mitochondria, what you can do with this thiolase, the beta-ketothiolase, I can bring them together, kick out a CoA. I've made this thing, acetyl-CoA. There's HMG. An enzyme here that alters, this case, the production of this thing, hydroxy-butyl-methyl-glycerol-CoA. What's happened here is you've got 2 acetyls coming from 2 CoA carriers. Down here, what's that incoming? Another acetyl. So that's 1, 2, 3 acetyls come together, kick out the CoAs. What have you got? This thing, HMG-CoA, that's active. Using this lyase, what have I got now? Kick out the acetyl, the reaction process, bless you. Now you've got acetoacetate, a ketone body, starting from acetyl-CoA. If I run down this carboxylase, I should say I get acetone. But acetone, you know from chemistry 1, hopefully, basically a solvent, very volatilized, so it'll vaporize. So you'll smell acetone on a diabetic's breath, or even Kipchoge's breath after he's done the marathon, because he'll be in a ketogenic state. Probably about a mile or 20 or so, kilometre 20 or so. Down the other pathway, we see this dehydrogenase. What have you got? Beta-hydroxybutyrate. Make sure you put an asterisk next to that. That's the major ketone body your brain will use the longer you're in that state, either ketogenic or diabetic. And that's why a ketogenic person or a diabetic person that's not controlling their blood glucose, you can smell acetone on their breath. That gives you a strong clinical indication already. Some of those monitors out there are there to detect things like acetone. So all those things we've seen all semester, acetyl functions, the CoA carrier, is going to keep you alive by fusing essentially 3 acetyls. Where are you doing this? Let me go back one slide. You're doing this, there it is, fatty acids. That is beta oxidation. Remember, you clip off 2 carbons at a time. What do you produce? Acetyl-CoA. So even to make ketone bodies from fats, you still have to go through beta oxidation. Where does that occur? The mitochondria. What does that produce? Electrons and protons to keep your liver alive. What state are we in? Fasted. And what's the other component of that? Stressed. Write it down. This is the stress state. And shall we have a look at the time frame it takes to go through this? We ready for the next one? Is that a yes? Look at the graph. Don't write anything yet, just look at the graph. Down here, day 0. That was the last time you had a meal. Look across the days to 40. Look at this time frame. Here's my blood glucose. Average individual, millimolar in this particular concentration range, drops down a little, keeps on dropping, slowly, slowly, plateaus. Why does it do that? Liver's still busy trying to make glucose no matter what. This just dropped a little bit. We're fasting now, we're up to a couple of days. What happens to my free fatty acids? I've stimulated them a bit more release of those. So it took a couple of days. What's the 5-2 diet work off? 2 days of fasting. So it's stimulating release of free fatty acids. So you run through that, you see your free fatty acids, and then after that we start to see our ketone bodies. There it is, acetone. You'll notice it tends to peak and then stop. Why? You're releasing it as a gas, hopefully through your oral cavity. Acetoacetate kicks up and kind of plateaus out, doesn't it? What about your butyrate? Boompa, all the way up. In terms of, in this case, millimolar. Let me go back to that time frame slide, which is there. We saw these events take over. We didn't see in here the ketone bodies, did we? It only took a couple of days, so we're out here. Gluconeogenesis is starting to back off. That's when your ketone bodies, just draw a little graph like that, beta-hydroxybutyrate, boom, takes off. You're in a ketogenic state. Now, we've said all the time that we don't see fats being used by the brain because of the blood. That chocolate had more in it than I thought it did. Blood-brain barrier. What's the blood-brain barrier? Blood-brain barrier. Don't they teach you that in Intro to Human Phys or something like that? Indeed, but it's also an immunologically privileged barrier. It doesn't allow immune cells in either as well, because your brain is bathed and washed through your CSF in a constant effluent state, washing out all the bad stuff. It doesn't have the same kind of circulation you're thinking of. So in that particular case, you don't have them going in there. There's a few characters that do some unusual things like astrocytes, but that's for another unit. So what do you think about a 5-2 diet? Would that be a stressed state diet, do you think? Depends on your definition of stress, doesn't it? It's fasting, you're inducing ketone bodies, so you could technically say it was more stressful than the body was used to, but at the same time you're driving your body into that training program. You're changing your gut size, receptor number, signal transduction. I would probably put it down as an early stress state. Now, if you did this each week for a number of months, would you consider that a chronic stress? Come on, debate me. Where's your opinion? Come on. Sorry? Yeah, because as I hinted before, you don't binge eat after 2 days of fasting generally. Why? Because your stomach shrunk a little bit. Your brain's getting the signal, now I'm full. What you are doing is training that all the time. So it's not necessarily that stressful chronically. It might be the first few weeks you try it, and I'd encourage you to try it because it's not an unhealthy thing. Make sure you have water during that time frame. If you have any precondition, don't do it. Get some advice. But think about trying it to see what it does to you and think about metabolism. Should you go into this state, 2 days of fasting into the metabolism exam? When these exams were on one campus, before we multiplied the campuses and put all the units across each campus, there used to be a, who was she? I think she was Sister Mary at Hawkesbury. Would go around with a lolly jar before the exams handing out lollies. Well, that was a nice gesture, but actually biochemically that's a very useful gesture, isn't it? A glucose rush just before the exam is going to do what for your brain? Help it work a little better, isn't it? So I used to carry on when she left, a big nice lolly jar, all natural lollies of course. Trouble is 3 campuses, 400 odd students, I can't get around every campus at the same time giving out lollies. I'd encourage you to think about having a glucose available for you or carbohydrates the night before. What's the one thing you should stay away from before the exam? Sorry? Indeed, fats, but also, sorry? Not too much sugar, but particularly caffeine, because that will alter your heart rate and what you think about. Can I move to the next one? The reason is I've had students on Hawkesbury who have overdosed on caffeine and the other one, the mother or whatever it is, the mother of all heart palpitations, drag her out, take her off to hospital. Don't do that. Should we have a break? Okay. And talk about some disease states. Okay. Are we all back? We're all back. For your report, Part B. Next few slides, I'll be making lots of hints, as I do through all the semester, on things that might be useful. Report Part B, what are the headings you need to use? Overview, research, diagnosis, treatments. What's the next one? Policy. And what's the other heading you probably should have? References. In report Part A, you got a genetic disorder or a metabolic disorder. Usually some dysfunction in a protein or enzyme activity, some point mutation, some variation in something. And for report Part B, you've got basically a drug, haven't you? Some kind of molecule, some metabolic manipulator that affects metabolic pathways. So you'll have the same headings as you see under here, but unlike report Part A, where I asked you for an EC number, which is a class of enzyme, bless you, that is a class of molecule. This time you're very unlikely to have an EC number. I think it's only 1 or 2 enzymes in that list I gave this year. All the rest are drugs of some kind, either derivatized, purified, isolated, but they are a class of molecule. They might be a lipophilic molecule, they might be a G protein coupler, they might be a hydrophobic molecule, they might be a beta agonist for a particular receptor. That's the class of molecule. No EC number for most of you. Is that kind of clear? So you don't need to look for an EC number, but you need to know the class of molecule. Yes, mate? And they're all different. They all act in different ways. Now, some act on enzymes, some act on different metabolites, some are substitutes for metabolites or substrates and or precursors in that context. You need to discuss those issues. I don't need the enzyme commission number for that enzyme, but it's useful, isn't it? It is, yep. It's useful to know what class of enzyme that molecule is affecting, because I'm trying to get you used to the real world. You know, there's a disease, a disorder, someone's developing a drug of therapeutic of some kind to affect that disease or disorder. And if that particular drug, as we were discussing a moment ago, has multiple targets, it can be used for other things, as some of you are finding out. The drug you've got may not just be for some metabolic pathway, it might be for drug addiction or something else. Because as we saw last week, drug addiction is the same pathway that's linked to food addiction and what your brain does, changing your metabolism. They're not unrelated, that's the problem. So you need to be already aware of the real world, not just this is metabolism, this is the drug, it treats me for this. It has side effects. You want to jot down the term adverse events. It has contraindications. You want to jot that term down. It does other things like many drugs do. The classic is Viagra, isn't it? That was a beta-2 derived drug to help patients with heart disorders, targeting the beta-2 adrenergic receptor I was talking about. What's it used for now? A lifestyle drug. Don't smile like that. It's a lifestyle drug. But that's because you can change the dose. Now, they're critical that you need to put down in your report. A classic biochemical experiment is a time and a dose response. You need to be aware of that, because under these headings, for example, how is it being used? How is the drug being used in research? Is it to target a particular disease or disorder, or is it a model for disease and disorder? Is it a way to find some other mechanism of action, to look at some other signal transduction pathway? Lots of drugs do that for us. And the more that's known about them, the more we can model them and understand we use them in our systems, in our research, to say, I've got this new one, how does it compare to the old one? Because it's well characterised. Jot that term down. Well characterised in all its mechanisms of action. Classic time and dose response. This is what it's about. That's what drug companies do all the time. The diagnosis, well, I asked you to look at the diagnosis for the disease. But there's 2 elements to this report. First of all, what's the disease this particular drug that you've got treats? Is it just one? Is it a multitude? And is that multitude metabolism related? If you're writing this report for somebody who knows nothing about, what have you got to do? Contextualise it. This drug does all these things, but I'm going to focus on the metabolic pathways because this is 300848 metabolism. Jones wants this. That is, Mark Jones wants that information. But you've got to contextualise it. What else does it do? And in that diagnosis, what's the disease that it's affecting in a metabolic pathway? The other component to it you've got to jot down is the drug itself. Does it induce a disease, a disorder in some kind? Because it's a higher dose, bless you, or a different dose regime. We see that with lots of drugs. When you go into the GP's office, they look at you, they'll get your body weight, they'll get an idea of what your sex is. That is your sex, not your sexual preference. Sometimes that's required. And from that, they'll decide the dose based on your body weight, your BMI, or whatever the case is. Too much for too long, what does it do? That's the question. It might induce a disease. You want to jot down an adverse event. Maybe nausea, vomiting, diarrhoea, whatever the case is, it's inducing a disease by itself. So there's the disease you're trying to treat and the drug that induces its own diseases or disorders. Those you've got to jot down. The same with treatment. When you treat with this drug for that particular disease or disorder, what's the regime? How many pills a day for how many weeks, whatever the case is. Depends on your particular drug. What's the delivery mechanism, which is what I have up here? Is the drug being developed so the delivery mechanism is not via injection, IV, maybe subcutaneous, maybe it's going to be a nasal spray or a gut delivery? Those can change, but it depends on the structural components of that drug, doesn't it? How you encapsulate it, how you deliver it. Those are the real world things you need to be aware of. And indeed, you should write this report succinctly in that context. The other bit, the policy. You know, every drug has a policy. In this country, we have the Pharmaceutical Benefit Scheme. That's the PBS. This drug might be used around the world with different requirements depending on where it's used. US, Europe, Asia, wherever the case is. PBS, if it's on that PBS scheme, someone's decided that it's worth subsidising because there's so many patients that are afflicted, which means you need statistics, which I'm about to go through in the next few slides, statistics on that information. But there's also a policy on delivery, whether it's an S4. You have to have a special licence to submit that or at least prescribe that to a patient. Codeine for a little while was off the shelf, wasn't it? You've all seen now that's been taken off the shelf. You need a prescription for that. That's an information database set that said that database said that that drug should not be free to buy off the shelf. There should be some advice given with it. Lots of drugs have those issues because of adverse events. You look to the US now, what's going on over there? Indeed, all those opioid issues over there, they're going to sue the pants off some of those drug companies because in the US, drug companies advertise directly on television. They're not supposed to do that in this country. You have to go to a GP, they will prescribe the drug. In the US, they'll say, oh, I've got this great drug, you should tell your GP to prescribe it for you. That's not a good thing because these are the sorts of things that happen. But that's what you need to talk about in this context. But not just that, the delivery of it. How it's delivered to the patient, not just by a courier, but administering it to the patient. Now, as I go through the next few slides, think about those things as I talk about diabetes and obesity particularly. What are the issues related to them? Can I move to the next one? Cool. Diabetes, as I said, is increasing. In some parts of the world, it's phenomenal. For instance, in Boston, there's a particular area where the rate of diabetes is almost 90% in young individuals, and they don't know why. It's a very affluent area of Boston. Despite all the education programs, all the good healthcare, because that's where those people can afford it, unusual in the US, but those issues mean that it's still increasing. And we're seeing increasing rates in the Middle East and developing countries, particularly as I had a student working from Jordan, looking at infant formula. Ultra-high temperature treated milk alters cow insulin, so no longer is it insulin, it's an antigen. That becomes an issue. We're going to see some issues of diabetes with how your islets work in a moment. 280 Australians develop diabetes every day, 1 every 5 minutes. This isn't a big country in terms of population. That's a lot. And that's why I keep hammering you about your metabolism. You're known now. You've been adulterated with metabolic knowledge. You should think about what you're doing. Try and pass on as much as you can. 1.7 have diagnosed and undiagnosed type 2. What does that mean? Preclinical or subclinical. These patients haven't been diagnosed absolutely, so they're running around with preclinical diabetes. That's an issue as well. And that can go on for long periods. And once it gets past a tipping point, there's no treatment that's easy for them. The cost, that's 14.6 billion for this country. That's what it costs us to deal with that healthcare. That's a lot of money just to deal with diabetes. Type 1, it's about 10%. Type 2, often late onset, that's 85%. That's huge. Which means the longer you go, the more likely you are to see it, particularly if you're not eating well, you're not exercising well. Yes, ma'am? The other 5%. What do you mean by the other 5%? Yeah, I realise that. There's a lot of undiagnosed characters as well, okay? And there's some that are, which we'll talk about later on, preclinical, there's pregnancy-induced diabetes, and there's a couple of other, I won't call phantom diabetic states, but states where the individual is not truly diabetic, but there's functions which are related to drug delivery, and there's 2 other mechanisms we'll talk about today. Okay? There's roughly 10% in that pregnancy-induced diabetes state. Yep. Sorry?
Anyone type 3? Type 3?
No, we their general consensus is they're sticking with, they've got rid of juvenile diabetes, that terminology. They'll talk about late onset diabetes, but generally it's type 1, type 2 and pregnancy-induced. Tends to make life easier because, as you'll see in a couple of videos, they have spillover effects in terms of their functional roles. What else? There's a gestational, that's pregnancy-induced. Please keep that in mind. 30% of Australians have diabetic retinopathy. Because you have this diabetes issues, blood glucose, ketogenic states as well, what you do is alter your blood vasculature, particularly small capillaries. Where are the smallest capillaries generally? In your eye. Which are going to be major issues for you longer term. Your retina particularly, which we'll talk about in advanced cell. Down below you see only 5,000 amputations. Particularly in the extremities, particularly the toes. The toes are some of the worst to deal with because of the blood circulation issues. But also you get weight loss. Now here's an interesting story for you. Have you ever heard the Banting and Best story? No? There's a doco somewhere around, you'll find that. Banting and Best, a couple of characters in the US trying to isolate insulin. They were using dog pancreatic cells, trying to get the tissue out of dogs to isolate the insulin. Those individuals finally got it out, or at least trying to get it out in the interim, and the lab head said, I'm going to bring in a specialist in purification of insulin, that is to crystallise it down, brings in this chemist. Chemist did not use a lab notebook. Did all his work. Oh, there's insulin crystals, that's wonderful, nice and pure. How did you do it? Okay, I'll do it again. Couldn't repeat it. Banting and Best finally cracked it. They got the purified dog insulin, so they got the Nobel and the new drug, that is insulin, to get it out. What's curious about that story is no lab book, no kudos, no record of invention. Big problem for that character. But it all came from dog insulin trying to deal with this individual. This individual got the first lot of dog insulin to save her from dying from this diabetes, the juvenile diabetes. Now that you're all depressed, can I move to the next one? The mellitus is one of those older terms that covers the diabetic state. Type 1 is insufficient production of insulin. Type 2 is the insulin resistance. We saw a bit of that with the receptor because the receptor doesn't work well. So think about, do you produce enough insulin? Let's have a look at some videos. I'm going to have to switch over to a different system. You can have a rest now.
Diabetes affects the pancreas, an organ of the digestive system.
Does that sound okay?
An important function of the pancreas is to make hormones that regulate blood glucose levels. Insulin is produced by beta cells, which cluster in groups called islets. Insulin is
Alpha, beta, gamma.
glucose levels. After a meal, glucose reaches the pancreas via the bloodstream and is released through capillaries into the pancreatic tissue. This triggers the release of insulin, which is stored inside the beta cells.
Like sparklers, isn't it?
The insulin travels to other parts of the body via the bloodstream with three main destinations: muscle, fat, and liver. Insulin helps these tissues to store glucose as an energy source. Shown here are muscle cells. Insulin arrives through the fine capillary network that traverses the muscle fibers.
Got whitewater rafting on that.
The surfaces of muscle, fat, and liver cells are covered with insulin receptors. When these receptors bind insulin, they signal to the cells to release special glucose transport channels onto the cell surface. These
Some of those GLUT2 transporters, GLUT1, GLUT3, GLUT4.
allowing the cells to store glucose as energy for future use. In this way, insulin acts to regulate blood glucose levels. In type 1 diabetes, a patient's own immune cells mistakenly attack the insulin-producing beta cells. Type 1 diabetes is referred to as an autoimmune disease because the body's immune system attacks its own cells in error. Over the course of the disease, a patient's immune cells will systematically but mistakenly kill nearly all the beta cells, shrinking the islet but leaving all other cells intact. The few beta cells that remain in the pancreas have a severely reduced capacity to produce insulin. The death of the pancreatic beta cells and the consequent inability to produce insulin is at the core of type 1 diabetes. Without insulin, the body cannot regulate blood glucose levels, and the high glucose levels damage many tissues throughout the body.
Right. Sid will be depressed again. Remember, that's type 1. Type 2 is going to look kind of similar, except we're talking about the receptor, but then there's a feedback to these islet cells. Type 1 generally develops early in life, used to be called juvenile diabetes. It's insulin dependent, the diabetes, its other name as well. Type 2 is insulin resistance. Think of the receptor. Yes, mate? Certainly. Is that better? Good. Yes, ma'am.
She said something about type 1 being an autoimmune disease.
Yes.
Now, it takes a while to diagnose someone with an autoimmune disease, right? So could people be diagnosed with type 1 diabetes, like, within what, 10 years of like, would they be able to be diagnosed with type 1 diabetes if they had the autoimmune disease? Like,
There's some early onset markers that people look for, and generally that's familial. So what you look at is the family. So if there's a history of diabetes in the family, usually the newborn is screened pretty early and then often monitored if there's a high risk factor. It means that, sorry?
Could they be diagnosed later in life as well?
They're often screened early. So that means that they're, particularly because it's juvenile diabetes, as I said, if there's a family history, they'll often monitor that young individual to see if there's early onset. Now, how many of you are doing advanced immunology? Probably a bit early for some of you. So talk about CD markers, cost of differentiation, and some of those markers related to the disease states. Sorry?
We just submitted a project on this last night for advanced immunology.
Yeah, exactly. Yep. Okay, good question. Let's get back to this one. So one is you don't produce enough insulin, the other is you don't respond to the insulin, at least initially. And I need you to keep that in mind because type 2 can do some other things which starts to look like type 1, which is why it made it so complicated to deal with. What's happening with your blood glucose? Well, you can't control it. And when you have high blood glucose, what do? You get thirsty because glucose loves water. It's trying to trap it all the time, trying to hydrate yourself. And what does that cause you to do? Urinate a lot. You're always thirsty, urinate. So you're constantly putting in water to deal with your glucose, which loves water, so it means you're constantly passing it out as well. You're also changing your overall production, things like ketone bodies and ketoacids. You're changing your blood pH. Here are some disease states that are clinical symptoms related, like Part B. What else happens in this particular state? Well, I don't put diabetes as a report topic because it's just too common, there's too much information. Your topics are a little bit more targeted, a little narrow to make your life more interesting, but more realistic. Can I get to the next one? Okay. Up here you're seeing fuel for metabolism in prolonged fasting. Is that a stress state? It is indeed. So we're beyond 2 days now, aren't we? We see this sometimes in type 1 diabetes. Here's the overall pathway, this big thing down the bottom here. You're going to write down hepatocytes or liver cells. What are you doing in this particular state? You're balancing all of these things: urea, glucose, ketone bodies, and incoming fats. What is our diabetic person dealing with? Well, the trouble is managing the insulin, managing the blood glucose. We've got to be managing those cells. So we see all these turnover rates. In this case, insulin also stimulates the fat cells to induce translocation of glucose transporters. You saw that beautiful little video? They pop up to the surface like we saw before. Snare snap proteins, there they are sucking up glucose. The key one here for this one, which you're going to circle, is this thing, AQP. Now that's called diabetes insipidus. Kind of an old name, but a new version of what it means. AQP, you're going to write down aquaporins. Aqua, like Aquarius, P-O-R-I-N-S, aquaporins. Your cells have them, pond slime has them. What do? These aquaporins are water pumps. They pump water out of cells. They're pumping it out of your cells all the time, trying to maintain your internal osmolarity of your cellular environment. Diabetes insipidus is where these guys don't work as well as they should do. Why is that? Because remember, glucose likes water. Too much glucose, lots of water. Here's my cells trying to pump it out, but I've got glucose trapping it. So now we see this insipidus event. What also happens long term, we've already seen with a ketogenic state, more ketone bodies. Beta-hydroxybutyrate starts to really crank up, acetone on the breath. Now acetoacetate does a little bit of work. So we start to see more complex versions of the diabetes the longer we go. But you can see fasting and diabetes look kind of similar, don't they? Especially type 1. Just about to move on. Just a sec. Think about this for your report. What is the progression of the disease? When you treat the individual with your drug, your compound, what is the progression of the inhibition of the disease symptoms? What is the rate of treatment outcome? Keep that in mind, because your dose and time course is designed to try and get the best outcome for the patient. Are we right now? Everybody else right? Can I move to the next one? Okay. Sorry? All right, type 2. Let's watch the video first. Afraid I'm going to have to kick out of that again. I know I've shown you the receptors. This one's a bit noisier.
Type 2 diabetes, also known as adult onset diabetes, is a metabolic disorder characterized by high blood glucose. Obesity is thought to be the primary cause of type 2 diabetes in people who are genetically predisposed.
Please note that, genetically predisposed, hence the familial information.
The pancreas is an organ which produces hormones that control blood glucose levels. The hormones that control blood glucose are produced by clusters of cells in the pancreas called islets. Here glucose is shown arriving at the islets via the bloodstream. The glucose is taken up by cells in the islet called beta cells. The beta cells respond by producing the hormone insulin, which lowers blood glucose.
ATP, potassium channel, calcium channel, out goes insulin.
In type 2 diabetes, high levels of glucose stimulate the beta cells to produce lots of insulin to lower the blood glucose levels. The insulin is taken up by the blood vessels for transport to muscle, liver, and to fat, where it allows those tissues to absorb glucose. Unfortunately, sustained production of insulin also leads to secretion of large amounts of another hormone-like substance by the beta cells. White blood cells, which live in the islet, respond to this hormone and consume it. We are now inside an islet white blood cell at a magnification of 250,000 times. The hormone, in combination with high glucose, causes production of free radicals inside the white cell. The free radicals activate a sentinel protein that originally evolved to protect us from microbial infection, causing it to unwind. The newly active sentinel proteins then aggregate with 6 other proteins to form a ring. Seven adaptor proteins then bind to the ring. The adaptor proteins work to capture specialized inactive proteins from the surrounding cell fluid, bringing 2 halves together to form the active whole, which is then released. This entire structure is called the inflammasome, and its sole purpose is to act as a platform for combining and activating these proteins. The newly active proteins then convert yet another small signaling protein, splitting it into its active form. This protein is the key protein involved in inflammation in the body. The inflammatory protein is then secreted from the white blood cells into the islet. Unfortunately, this inflammatory protein causes death of the beta cells. Over time, beta cell death causes the islets to shrink, accelerating disease progression. As the islets are now greatly reduced in size,
They cannot produce enough insulin to control blood glucose levels. Over time, high blood glucose causes damage to many different tissues throughout the body. What originally evolved as a defense mechanism against infection now seems to be a driving force for inflammation in type 2 diabetes. Chronic diseases associated with inflammation are the most common diseases of ageing in the Western world and represent our greatest health threats in the 21st century.
Now you're more depressed. But keep in mind two things for that. Remember, type 1, you don't produce enough insulin to cope with the glucose you've got. Type 2, you produce lots of insulin, the receptor's not responding. Because you've got so much insulin, you start to induce this inflammasome, which then induces inflammation, which reduces the number of islets, which produces less insulin. Does that kind of make sense? So that's why diabetes is so difficult to deal with in terms of managing, and why it's been so complicated. That's why you've got different names for it at different times. Yes, ma'am?
Would you get the islets back, but can they recover?
Depends on your age. There's some instance in younger individuals, if you can inhibit the induction of death of those islet cells, recovery from stem cell populations is more reliable, but not absolute. Older individuals, most of the data I'm aware of is that you generally don't induce more islets once you're past sort of the 40, 50 age bracket. Sometimes 20 or 30, depending on your genetic background. As you've heard, there's a genetic background component to it as well, which is related to how these proteins interact. Does that answer your question? Yeah. Okay. So type 2. Most of these characters, 90% of them, are type 2. 300 million worldwide. That's a lot of people. That's across the world. In this case, it's the resistance to insulin. What happens? You keep making too much until you induce that inflammation event with your inflammasome. Tends to happen later on, but also most obese people don't develop type 2 diabetes. Why, do you think? That stumped you, didn't it? Talking about obesity and diabetes, kind of interchangeable. There's issues there. Why do you think? Indeed, there's a lot of genetic predisposition to it particularly. But you can see events in there as well. What I want you to notice is this term, cluster of symptoms. That's in there for a reason. It's for Part B, your report. What are the clusters of symptoms? In Part A, I asked you to talk about differential diagnosis. We're not worried about that so much now. What you're worried about is my drug going to treat this cluster of symptoms? And of those symptoms, abdominal obesity, I said that was an issue, didn't I? A lot of fat around the belly. Why is that? Particularly in elderly patients, particularly males and some females. Belly fat, you've heard these, remember the ads from 4 or 5 years ago maybe? They put a tape measure around somebody. That becomes an issue because is that fat used for much? Not normally. That's why you want to control that belly fat particularly, because that has a high incidence and correlation to onset of diabetes and other diseases as well. Triacylglycerols, TAGs, remember those? How much of those? In not just chylomicrons, HDLs, VLDLs, low HDLs, remember those? What about high blood pressure? What does that tell me? Heart's pumping away and all this blood vasculature I can't get through properly. I'm inhibiting functional activity of capillary cells. The elevated blood glucose, which may not get to full-blown diabetes. You can have patients subclinical for years. You might want to note that term. So individuals can go years with subclinical diabetes in ways they tend to manage either by diet, naturally or knowing or otherwise, but it takes time sometimes to develop those disorders. Then we start to see inflammation. We saw that inflammasome. Why? Immune cells targeting to target. We saw in type 1, immune cells already targeting. What is that? An immune cell disease. Autoimmunity occurs a lot, particularly in type 1 where the individual is not training their immune cells to defend themselves, they start attacking themselves, which is part of the issue that hopefully covered in. Did he cover that? Cool. Should have. All right, sorry, we done with this one? Now, what's the long-term effects of sugars? I kept saying all semester about glycosylation. My only fault was I didn't actually check this video works on this system. Cross your fingers while it updates. What is glycosylation? Glycosylation is putting carbohydrates on molecules.
Isolation, adding sugars.
He's answered it. How do you do that and where? Lots of videos today. I had to wait till the end of the semester for all these videos. How do you do that? Well, in your notice ER, and rough ER is doing what? Ribosomes making things, yeah. We're going to have a ribosome come in a minute. We're going to have our polypeptide come, but in the lipid bilayer, which is lipids, this green thing here, we have this dilocal phosphate. Phosphate's linked to a lipid molecule, and these hexagonal structures are different sugar moieties. Now, if you're on a high sugar diet and not using it for work, you'll make fat, bless you. But you've got all this excess sugar that's running around, and you start making all these branch chain sugar polymers. And immune cells, I kept hinting all semester, do that a lot. Because when you have glucose, branch chaining, you can have lots of hydrogen bonding. They get stickier. What's this character doing? Well, we're about to see a ribosome come in. I won't spend too long on this animation. Here comes a ribosome with a polypeptide. What happened? This is post-translational modification. That branching system is now stuck on that polypeptide. Can be unique amino acids. And you don't have to watch too carefully, but notice as we start processing that polypeptide, moving it from different parts of the cell, it might be a receptor stuck in the membrane, like a CD marker, an immune cell marker, things we talk about next semester particularly, more and more sugar molecules which actually then sit on the cell surface, available to the external environment. That's like Velcro. Everything sticks to it. So then it sticks to things it shouldn't stick to, like your islet cells, your beta islet cells. That's what type 1 tends to be. Too much sugar for a juvenile diabetic, and the genetic predisposition means they drive themselves into inducing immune cell inflammation, lysis autoimmune disease. And again, you want to note this is because of excess glucose in the diet, beyond what you normally require. And you can see there's all this branching going, and this is just an example of all kinds of branching. Just think of that as Velcro. That's as sticky as now for these cells. That also changes your hemoglobin. What was that? That big protein molecule with the heme function we talked about at the beginning of the semester. What do you do to it? Because it's relatively abundant and because your red blood cells don't have mitochondria, they're busy just carting this stuff around. What happens to that? You often get excess glycosylation of hemoglobin, which you disrupt the hemoglobin's ability to transport oxygen. What do we see in diabetic patients? Amputations. Where do we see it mostly? Peripheral tissue, particularly in the toes and in fine capillaries like the eyes. Not so much the amputation. Because you can't get the oxygen to those cells and tissues as well because the hemoglobin in your red blood cells is not working as well. It also increases cardiovascular disease. But note these small blood vessels put down capillaries, particularly very fine capillaries. But it also screws up your nerve cells so you don't think as well, you don't move as well, your balance starts to get out of whack. All of these issues start to compound in these individuals. And we start to then see renal failure. And is the kidney important the more ketogenic you become? Yes, it is. It's got to start working to support you. Are you really depressed now? Is that from metabolism or just the diabetes? Can I get to the next one? Don't answer that question. Yeah. Are we ready for the next one? Is that a yes? Okay. Look at this table, and what do you see off to the left? Drugs, activity, mode of action. You'll note treatment, underline it. How do you treat the patient? This comes back to your report part B. Is it the drug that you've selected alone, or is it used in combination with something like exercise, diet changes, some other drug as well? Is it used on its own, or is it used in combination? Write that word down, combination or cocktail therapies. What do these things do? Well, weight loss, reducing intake, exercise encourages activity in tissues and cells, bless you. Here's some drugs, things like sulfonylureas, we saw those before, didn't we? They can affect things like insulin release from your beta cells if the insulin signal from potassium through the potassium channel, blockage, calcium release doesn't work too well. You can bypass it. So this thing, the sulfonylurea, changes the potassium channel, which changes the voltage potential, which releases insulin. Here's a few other things. Now, these names here, what do you know? They affect PPARs, particularly the gamma. You might find one of those or two of those on the list I've given you. If you're lucky, you selected it. Others, things like these characters, glucagon-like peptide, they're mimics. Write that word down. They mimic somebody. Remember I talked about partial agonist, partial antagonist? They look like a hormone or an active agent. They work via receptors, but they kind of mimic it. They also have a half-life. They might alter the function later on. Now, why do you think they all have crazy names? Could you pronounce the one you selected? You think you can. Most people can't. Why do you think they have crazy names? Think about metabolism. If they're all AMP kinases or receptor binding proteins, it'd be a bit of a nightmare, wouldn't it? It's mostly marketing to make sure the name is so distinct it's not prescribed somewhere else by accident. That's a clear thing for marketing. That's why your name is crazy. Your report part B, you should look for the true biochemical molecular name, the chemical name, not just the drug name. Not just the drug name. What's its chemical name? That'll give you its class. Is everyone clear on that? Its drug name might be a generic. You know about generics, don't you? Are we done with this one? Not yet? And you thought you'd finished with report part B already. Are we set now? Okay now? Before I leave this slide, what do you notice about that heading up there? Direct targets. Your drug might have indirect targets, often what we call spillover effects into other components. If it does, you need to articulate that it does, but focus on your area. How many words have you got? 1,000. So make sure you contextualise but focus. That's a key thing in writing a briefing, an executive summary or a brief report. Not prattle on with garbage forever. Can we move on? Good. Now we've got some excess calories. We saw what happens to you in your cells, glycosylation starts to affect functional activity. What you've got now is you've built up all those fat reservoirs, you've put your money in the bank. I'll let you write and I'll talk you through this slide. But underline that first phrase. Fat cells unable to cope with more incoming fat. The warehouses are full. What are you going to do with all that fat coming in with the meal you've just had? Cell division and differentiation takes a few days, not a few minutes or hours. was nice of her, wasn't it? No. I mean, actually, that's my aim, to make you think about what these issues are. Forget the metabolism in the first half of the semester, only short period. Think about the implications of all this stuff, what it does to you and your wallet, because you're paying for these healthcare issues. Well, maybe not yet, but you will when you start paying taxes. Okay. Can we talk about this one now? Some of you are paying taxes. Yep. Okay. You've just had a meal. If you're a lean person, generally what happens to you? You generally have small fat cells, small adipocytes. You've got the same rough number that you've had for most of your life. What are you doing in there? The triacylglycerols in your diet pretty much match what you turn over. What did I say about fats at the beginning of the semester? They're constantly turned over. They don't just sit there for the rest of your life. You refresh them, because fats will oxidise like they do in the fridge. So you want to refresh them all the time. So your incoming is always being turned over with those cells. Keep in mind, they're also going into lipid bilayers. New lipid membranes, vesicles, cells, stem cells, replacing your population all the time. There's this constant fluxing and turnover. So that's pretty much equal. When you start to increase the amount of fats coming in versus what you've got in terms of turnover, the catabolised ones, what do? You put it into your fat cells as storage. They increase in size. What do? Increase your waistline generally. That's not a bad thing for winter, for example, or if you're going to fast for a longer period. We've seen that's not a big deal. What's happening in your muscle? Well, it's still using glucose, it's using some fats, there's still refreshing and turning over, that never changes. You get down here, what have we got here? Pro-inflammatory state, where what's going on is your fat cells now are rather large. You've induced, you want to jot down, induced division. And that process is also inducing a protein secretion called MCP1. It's a macrophage chemotaxis protein. It's saying, we've got a lot of stuff in here, that's not a healthy thing. So here we have this pro-inflammatory state, this chemotaxis protein. Now it's being secreted by this. There's still fat turnover, there's still glucose being used in our muscle cell. Now we get to a chronic inflammation state. Please note this is not the islet cells in your beta cells in the islets, get that right. It's not the beta cells. This is your muscle cells and the fat depots around them. Incoming food, just after a big meal. You've been on one of those competitions trying to stuff as many hot dogs in as you can. There's all the fat running around. It can't get shoved in fast enough. There's still constant turnover. You've gone past this pro-inflammatory state. Now you're chronic. You're eating too much all the time. What do? Trouble is, I can't store all that fat. I've just induced MCP1. What do I start seeing? These cells, tumour necrosis factor cells. TNF-alpha is the stimulate for them. What does that do? They're the same stimulus we see in tumour cells to say this cell shouldn't be here. You're inducing immune cells, like you saw with that islet, to start to come in and attack them. We start to see effects where now we start to see lipid build-up. You write down here free fatty acids around muscle. You're going to jot down particularly the heart. The blood vessels around the heart build up more fats. That's atherosclerosis. You're likely to have a heart attack because you're ingesting more than you need. You've induced MCP1. Those macrophages gone into that fat cell has secreted tumour necrosis factor alpha. That stimulated release of free fatty acids. Jot down free fatty acids. Yes, glycerol go out. Someone will use that to make glucose or something else. But those free fatty acids are running around on BSA. It's going to alter PPARs. But those free fatty acids can't go anywhere. There's nowhere to go. Back to the liver, stored again, sent back again. It's like I'm going around in circles. My warehouse is full. It's told to empty out because of my TNF-alpha and my macrophages. What does it do? It then gets dumped out. There's a muscle cell, lots of fat running around, and it starts sticking to muscle, sticking to blood vessels. You start blocking your arteries with fat now, free fatty acids particularly. You're inducing more of this inflammation event. And what you also see, and you want to jot down, all of this fat, just like the fat we saw in the sink at the beginning of the semester, that concept is wrapping around your muscle cell, covering it. We saw those glucose transporters pop up in that animation. Well, there they are popping up. Now you've got fat on top of it. Can't see the glucose, can't suck in the glucose, can't get a response. I've layered cells in lipids. I can't respond the way I should do. Everything's coated in fat now. What should you do? Grab the Sunshine detergent, whoosh it in, try and wash it off? Might kill you, mightn't it? That's the kind of thing that has to happen. So what you're seeing is fat build-up, is what is termed underlying ectopic, outside the cell, outside the tissue, building up around the cell, blocking cellular function. No more receptors available, no more glucose transporters. Bless you. You've coated those cells in fat, which then induces, you underline this, insulin resistance, because now I can't get my insulin to my receptor to put glucose transporters on, altering functional activity of your muscle, right down particularly your heart. Wow, it's a depressing day, isn't it? You'll be on the 5-2 diet starting today. Can I get to the next one? Some data slides, which more for your interest. Don't write anything, just listen for a moment. These are not critical for the exam. You know, obesity in pregnancy, and I'm putting this up to remind you of report part B to some degree, to remind you of the relationship, to remind you that you're young people, most of you, and in that case you might be having children at some point in the future. From the US, bit of data out of there before Mr. Trump, 23% of women are obese prior to pregnancy. Your epigenetics is actually going to then be visited upon your children. What you eat, what you do, is going to have a consequence to them before they come into the world. So you need to consider that process as well. Remember that old saying, the sins of the father are visited upon the son? It's not just some fairy tale, it's epigenetics. Whatever that individual's experienced is going to run through to the genome of that individual that's coming out of there. It's increased over the last 20 years. That's data from last year. So it's increasing fairly rapidly. 1 in 5 children are at risk of obesity, heart disease, a child at risk of heart disease. I mean, that's almost phenomenal. Diabetes, cognitive, underline, and behavioural difficulty. I don't mean you underline particularly, I mean just underline it mentally. Because of these issues, the brain doesn't develop properly. That means the individual is not as capable. They won't be in this room with you. They're not going to make it. They're always going to require constant care, particularly ADD patients. Constant care and responsibility for them. You see their neurodevelopment disorders, autism, for example, classic in those individuals. So what you do has an impact on the next generation and so on. Keep that in mind. This ADHD or ADD, I know patients on it in the US. They're taking medicinal marijuana. Well, I've hinted at you, marijuana drops your IQ 10% just like that. There's no recovery from that. That's what that drug does because it alters brain function, neuronal activity. Those things are an issue. You look at what's going on in the US. I look at the American news all the time, every day, twice a day, because that has an impact on what happens over here. Women in gestational diabetes, around 26 weeks, to come back to that question earlier, around 26 weeks, how far are you through gestation at that point? About 2/3, which is when a fetus starts to really develop. The rate of differentiation is much higher, particularly brain function, which is normal. And we found this group here. Now, what I found was interesting. It was at that time, when the brain is getting more developed, these characters from UCS Carolina made this comment, which I put in a quote. Now, I rarely do quotes. I'm not a fan of them. But this quote, thought, shit, there appeared to be not a technical dose response. That's a classic biochemistry. Increase the concentration, increase the dose. That's straightforward. But a relationship in severity, how severe these patients have their autism or disease state as a function of what's been experienced by the mother at and around the 26-week period. So you can't wait till the end of pregnancy to start fasting and changing your diet. It's before you even get pregnant, if that's the case. That's the impact that you'll see through the life of that individual. That increases the earlier onset, the more severity, and the risk of things like autism. which means now you have basically, if you have not gone through this process, these individuals have found you have basically condemned that child to autism just because of diet, functional activity during brain development around that 26-week period. You really depressed now? Good. Yes, ma'am. Let's keep names out of this and relationships, yep. And individual, yes.
But the rest of my mum and dad's children are all fine. There was no evidence of intellectual disability. So what happened then?
There's often genetic predisposition and, as I said, epigenetics. Remember, there's a random event of egg and sperm. Talk about that next semester, how the sperm actually gets the nucleus in there, which might cause disruption. Remember the chiasmata you hopefully learnt about in cell biology, crossover of DNA. That particular individual went that path, that's the way they went. Everybody else was okay. That makes sense. So it doesn't necessarily mean everybody's going to have that issue. What this is saying, what I'm trying to get across to you, is it increases the severity, the rate that's likely to happen. That becomes the issue. Does that answer your question? Yes, ma'am. I've seen some data on that, and discussing that with some colleagues just a few days ago. There is some rudimentary evidence, but the trouble is abortion, or whatever the case is, or reabsorption of the fetus can happen for various reasons, not just drug-induced or fat-induced. Can be the wrong crossover, the wrong kind of combination, the wrong time. It's really difficult to pull that data out, unfortunately. You need to know absolutely what the patient's going through for that data set. So there's a lot of conjecture about that at this point. For later onset or later incidence of fetal abortion, there's some links to it, particularly when you see the process occurring around the 26-week period. And that's usually when the fetus gets busier pre-programming, differentiating more in its cells and tissues, and it becomes more vulnerable, which I don't talk too much about in advanced cell, but you know, those developmental phases are critical. Does that answer that question? Okay.
Can be related back to other disorders like Down syndrome?
No, Down is you've got 2 chromosome 21s. And that happens as a function of age, because often if the female who's beyond the 40 age bracket, the incidence or the rate of genetic disorders, mutations in the crossover of DNA between egg and sperm increases significantly. And the quality of the egg genome after age 40, roughly, just drops off. The quality is like that. So after age 40, then the likelihood of 221s, Down syndrome, is not uncommon. It increases actually with age. Does that answer that question? Okay. All right, we're done with this one. What about your mitochondria? What are they supposed to do? Keep you working. Don't write anything. This is for your edification, just to really put the icing on the depression cake. Coming back to that question a moment ago about eggs from obese mothers had mitochondrial defects. What do we notice about mitochondria? We could have point mutations. The DNA has their own mitochondria. The more they divide, the more likelihood. What did you see in that video about Ross species? Reactive oxygen species, not enough glutathione to try and limit that effect. Ross species damaged DNA, particularly in mitochondria. In that particular incidence with obese individuals, we start to see those events start to go more and more into the patient, that is, the infant. I've already dropped the hint to you that in advanced cell we talk about having a mitochondrial disease in one patient. So here we have 2 parents, mitochondrial disease. The mitochondrial DNA comes from the mother. How do we deal with that patient? Well, we take the fused nuclei, the egg and sperm nuclei. We find another donor that has a healthy mitochondria, pull their nucleus out, put their nucleus in. Now that's my infant. My infant, for those parents, their nuclear DNA, somebody else's mitochondrial healthy DNA. They are out there in their teens already. Somebody's healthy DNA for mitochondria, but their parents' chromosomal nuclear DNA. Does that make sense? That goes on a lot. We talk about that. This is just telling you that that's the issue now. It's been understood in that context. And particularly we're seeing it in obese models, animals, the same issue. So obesity then starts to progress to the next level. Keep in mind this imprinting effect. You know, if this is my level of activity, what I do, then I pass it on as epigenetics. My microRNA tell me this is what I should do, what I'm used to. But also you want to jot down for yourselves, it's about your familial lifestyle and activity, what you're used to. Now, is your fridge full of chocolate bars and Cokes and Fantas and stuff like that, or is it full of fruit and vegetables? That's what you're used to. And that will change what you do, which then imprints to the individuals that are coming next, aren't they? So you've got to consider what that does. You're all now going to be graduates either this year or next year, aren't you? University graduates, you should know. I've just made your brains bigger. Hopefully they won't explode. Which also means as you age, they won't shrink as much, hopefully. But it means you know enough to be dangerous, but also know enough to advise others of the things you should do. Here's another interesting one. Silbrenol, which is a drug, BGP-15, reverse these effects at translational levels. I keep talking about gene expression. Translation is what? RNA to protein. Who affects RNA to protein? MicroRNAs. Those are epigenetic terms. Keep that in mind. What you experience in your parents is passed on to you in that context. And this occurs particularly in the ER and the mitochondria as well. What's the ER do? Think of rough ER, translating that molecule from an mRNA to a polypeptide and the glycosylation, which kind of rounds off metabolism, doesn't it? Except for this one. Now, this one you might need to keep in mind. This university has a plethora of microbiology units, doesn't it? Everybody has to do one or two, I don't know why. In my undergrad days, you just did one, that was plenty, and that was more than enough for me. What's important here is the relationship now to what your gut does. I said at the beginning of the semester, we talked about those characters in there that take advantage of what you ingest. You've all seen those probiotic bacteria. There's like millions of those on the market now as well. But what we see now, coming out more and more, is obese individuals and lean individuals have different gut microbes. They process things differently. Wouldn't that make sense? Oops. Wouldn't that make sense? If my fridge was full of fruit and vegetables, and your fridge is full of chocolate bars and Fanta and Coke, wouldn't you have a different gut biome to deal with it? Of course you do, which means it's going to change how you process it. Some of these guys alter activity. Now, we saw propionate, we saw things like ruminants deal with those kinds of fats. Well, some of your microbes deal with them as well. Not so much in you don't have too many, you don't have a rumen. And propionate is known to act on GPCR. What's a GPCR when it's at home? You get a chocolate bar if you get it right. Actually, I'll give you the $2 to get... There's your $2. You can go down and get a Mars bar or whatever. It's a G protein coupled receptor. Get some new running shoes. I made a promise. I keep my promises. G protein coupled receptor. He's going to buy a Mars bar or a Kit Kat and share it with you. A G protein coupled receptor, are there classes of enzymes or drugs that affect GPCRs? They're in R&D. So we're seeing our gut now with different activity levels. You also see macrophages. Your gut has macrophages all the time trying to defend you. But if you fill it full of fat, abdominal fat, that's going to alter its functionality, isn't it? But also going to alter the turnover.